Dear students, today we will start with new type of reactions, that is named reactions. So this will be our first lecture in a series of lectures on these named reactions, and first I have selected a very important reaction, that is BIRCH reduction. BIRCH reduction is basically an organic compound wherein the aromatic compounds, they are converted into hexadienes. For example, if we are having benzene, then in presence of sodium metal or lithium metal or potassium metal, in presence of an alcohol, in using liquid ammonia as solvent, can be converted into these types of 1,4-cyclohexadienes. And this reaction can be extended to other aromatic systems like naphthalene also, where we can get dihydro and tetrahydro products under the same conditions of using sodium metal in liquid ammonia in presence of an alcohol at low temperature. And this reaction, if we compare with catalytic hydrogenation, so in case of catalytic hydrogenation, if we do the reduction, then all the carbon-carbon double bonds, they are reduced to give us a cyclohexane. So we can say this is a very good selective catalyst wherein only one of the carbon-carbon double bond is reduced. So we can say this is an example of partial reduction of aromatic systems. As far as mechanism is concerned, the mechanism given by BIRCH was that when a solution of sodium in liquid ammonia is there, then it exists as this type of salt which is called as electrolyte salt sorry where we are having free electrons which can participate in the reaction, and this solution of sodium in liquid ammonia is highly intense and it is blue in color, and these solvated electrons they add to the aromatic system to give a radical anion. So what happens is the electron from this solvated liquid ammonia sodium salt attacks the aromatic ring, and we will get this type of radical anion. So one carbon will be having 2 electrons and it will be having negative charge, and other carbon will be having a single electron. So we will have the formation of a radical anion, and this radical anion will interact with the alcohol present in the system, and it will abstract one proton from the alcohol, and that proton will be added to the negative charge anion formed on the aromatic system, and we will get this type of radical formed. And then this radical will again take one more electron from this electrolyte salt which has been formed from the solution of sodium and liquid ammonia, and this will also become an anion. And then again this anion will interact with one more molecule of alcohol, and proton will be abstracted by this anion, and we will get these types of 1,4-cyclohexadienes as the product. So this is how benzene will be converted into cyclohexadiene, 1,4-cyclohexadienes. Now further, the mechanism was elaborated that if we are having substituted aromatic systems, whether electron releasing groups they are attached to the aromatic system, or electron withdrawing groups, they are attached to the aromatic system. Now first mechanism is when we are having an electron releasing group attached to the aromatic system, and that electron releasing group may be methoxy or some alkyl group like methyl, ethyl, butyl and so on. Now when an electron releasing group is attached to the aromatic system, then the electron from the liquid ammonia sodium metal solution that will attack the aromatic system, and originally BIRCH has thought, the mechanism given by BIRCH has thought that the attack of the electron will take place in such a way that the radical anion that is meta to the methoxy or alkyl group. So this is our methoxy group, either this is meta or this is meta. So radical anion will be formed at the meta position to the methoxy or alkyl group. Now if this is the radical anion, if this radical anion is formed at meta position, then the last step will take place with the protonation of a cyclohexadienyl anion, this one at the ortho position. But later on in 1961 the Huckel computations they proved that the mechanism suggested by BIRCH was not correct, and correct mechanism is that this electron will add at the meta position and this type of radical anion will be formed where the negative charge is present ortho to the methoxy group. And this negative charge, because of the presence of this negative charge at the ortho position, the first protonation will take place at the ortho position. So this anion will take up proton from the tertiary butanol, and we will get this type of protonated cyclohexadiene species where the protonation in the first step will take place at the position ortho to the methoxy group, or if it is any other electron releasing group, that means ortho to the electron releasing group. And in the second step, then this radical will take up another electron and this will become again anion, and then protonation of this anion will take place with the with another molecule of the alcohol, and this is how we will get the cyclohexadiene products from the BIRCH reduction of this anisole moiety. So basically the product formed from this to this is same as suggested by BIRCH, but the only thing is the mechanism which was given by BIRCH was that first anion is formed at this place and this is protonated, whereas actual mechanism is that the protonation first take place at the ortho position and not at the meta position with respect to methoxy. Similarly, when the electron withdrawing groups they are attached to the aromatic ring, then the mechanism followed is such that the anion is formed at the para position. So initial protonation of the tertiary butanol with this anion will take place at the para position rather than at the ipso position. Ipso position is the carbon to which the electron withdrawing group is attached. So that means in case of electron withdrawing groups, attack of the electron will take place at the ipso carbon, and here we will be having a radical, and movement of this pi electrons will lead to the formation of a carbanion at para position, and this carbanion will take up proton from the tertiary and protonation will take place in the first step at the para position rather than ipso carbon. Then this radical will this radical anion with the reaction with the tertiary will be converted into this free radical, and this free radical will again take up one more electron from the electrolyte salt solution present because of the presence of sodium metal and liquid ammonia, and this will give one more electron, and this will be converted into this type of anion, and this anion is stabilized because of the presence of this electron withdrawing group, say carboxylic acid. This can move to this position to create a carbon-carbon double bond, and this carbon-oxygen double bond can be converted to O negative, because this being an electronegative atom can accommodate this negative charge more easily as compared to the carbon. So this carbanion is stabilized due to the presence of this carboxylic acid, and then this this carbanion can either undergo protonation on reaction with one more molecule of the tertiary, and we will have this type of cyclohexadiene as the product, or these can react with alkyl halides. So what will happen is this will move to this position, and this carbon being having a negative charge will act as a nucleophile, and this nucleophile will attack the alkyl halide carbon of the alkyl halide, and halogen will be eliminated, and we will get the alkylation product in case of Birch reduction. So either we can have proton from the alcohols or alkyl group from the alkyl halides. So either only reduction will take place, or alkylated reduction followed by alkylation can take place if we are using alkyl halides in addition to the sodium and sodium in liquid ammonia. So difference between the products in case of electron withdrawing group and electron leasing groups, you can see over here that if we are having a product where R is an electron releasing group, then these types of hexadienes are formed, where the R group, either in case of electron leasing group it can be methoxy or methyl or ethyl and so on, that will be attached to one of the double bonds, whereas when this is an electron withdrawing group, then least substituted alkenes they will be formed. Here more substituted alkenes will be formed. So this is how we can differentiate between the Birch reduction in case of electron leasing or electron withdrawing group, and such type of situation is called as Regio selectivity, because the product formed is placement specific. So that placement preference of groups during the reaction and in the final product, this is termed as Regio selectivity. So depending upon the type of the functional group present, whether it is electron releasing group or it is electron withdrawing group, we are getting the type of product. That reaction take place on a specific region of the molecule. That is why the Birch reduction, this shows Regio selectivity also. So location on the ring where the radical anion is protonated, will determine the structure of the product. And the radical anion formed, that will depend upon whether we are having an electron leasing group attached to the aromatic system or electron withdrawing group attached to the aromatic system. Then the BIRCH reduction also shows stereoselectivity, that only one of the enantiomer possible is formed during the reaction. That type of reaction is called as stereoselective. If out of the two enantiomers possible as product, only one product is one enantiomer is formed as product, then we say that reaction is a stereoselective reaction. And BIRCH reduction also shows stereoselectivity. For example, when the reduction of this chiral benzamide, where this group is alpha with respect to this ring, when this is reacted with potassium metal in liquid ammonia in presence of tertiary butanol, and we are using alkyl halide in addition also. So when we use alkyl halide, that means the initially formed product in the BIRCH reduction will undergo further alkylation to give us alkylated product. So in the first instance, due to BIRCH reduction, because of the presence of this electron leasing group, more substituted cyclohexadiene of this type will be formed, and then this cyclohexadiene will undergo addition of the alkyl halide, and we will get this type of stereoselective product. And it has been found that diastereoselectivity of this product formed is 100:1. That 100 times product formed is where this carbon is beta, and 1 time is when this is alpha. So diastereoselectivity of this product is very high. So we can say this is the best example for stereoselectivity of BIRCH reduction. And this product formed, diastereoselective product formed, is used in the synthesis of apovincamine, which is a natural product, optically active natural product. Then the mechanism for BIRCH alkylation, as I have told you that in presence of an alkyl halide, the carbanion which is formed during the BIRCH reduction, this undergoes nucleophilic substitution reaction to form a new carbon-carbon double bond. And this new formation of carbon-carbon double bond is called as BIRCH alkylation in this case. So for example, if we are having some electron withdrawing group present on the aromatic ring, such as carboxylic acid, for example, say this one, this is a derivative of carboxylic acid, then the cyclohexadiene which is formed is least substituted. Olefin is generated when it undergoes cyclization. So if I react this aromatic system in presence of lithium in liquid ammonia and tertiary butanol in presence of this dibromide, then alkylation of the carbanion formed during the reaction BIRCH reduction will take place, and this alkyl halide, this carbon will act as a nucleophile, and one of the bromide will be removed, and we will get this type of alkylated product. And this type of alkylated product will be formed with the least substituted olefin. We can see that the alkylation has taken place at this carbon, which is not the carbon present on the carbon-carbon double bond. Whereas when we are using electron donating substituents, say methoxy group, then the product formed will be the most substituted olefin. So for example, if we take this aromatic system where we are having one methoxy group which is an electron releasing group, and this is converted into this type of alpha beta unsaturated ketone as the alkylated product. Now how this is formed? As we know, in the first step, in case of electron releasing groups, we will get the attack of the electron at the meta position, and we will get this type of carbanion formed, and this intermediate can act as a nucleophile, and this will undergo nucleophilic substitution. This goes to this place, and this carbon will act as a nucleophile, will attack the carbon of the alkyl halide, and this bromide will be removed, and we will get this type of intermediate cyclohexadiene, and this will undergo hydrolysis and decarboxylation. This type of cyclohexadiene will be formed, and this first will undergo hydrolysis at this enolic form, and this will be converted into a ketone, and then this ketone will undergo decarboxylation like this to give us this type of alkylated product. Then modifications in BIRCH reduction. The use of liquid ammonia is quite troublesome and time consuming. So in some of the cases, this liquid ammonia has been replaced by some other solvents like THF or a mixture of N-propylamine or ethylene diamine, and sometimes a mixture of these two, or sometimes ethylene diamine has been used independently, and this mixture of N-propylamine with ethylene diamine, this actually is a modification of Banks's reaction. So these conditions can lead to the formation of partially reduced product like in the BIRCH reduction. So when naphthalene is reduced in presence of 5 equivalents of lithium metal and 5 equivalents of ethylene diamine as the base as the solvent in presence of tertiary butanol and N-propylamine, then mixture of N-propylamine and ethylene diamine, this is used as an alternative to the liquid ammonia. So when this is done, this is partially reduced to this type of partially hydrated naphthalene as the product. So we are getting 1, 4, 5, 8 tetrahydronaphthalene as the product when lithium is used in combination of ethylene diamine and N-propylamine. This is called as isotetraline, and in addition a small amount of tetraline, that is 1, 2, 3, 4 tetrahydronaphthalene is also formed as a byproduct when we are using regular BIRCH reduction reaction. Whereas when we use modified condition, that is Banks's reaction conditions, then we are getting this as the product, isotetraline. 1, 4, 5, 8 tetrahydronaphthalene is formed as the product. Then some common applications of BIRCH reduction. So if we are having this type of aromatic system having a side chain of alpha amino acids, you can see that this is an electron leasing group. So Birch reduction of this type of aromatic system will lead to the formation of these types of cyclohexadiene salt, cyclohexadienes with alpha amino acid side chain. And when this is hydrolyzed in presence of an acid, then this vinyl ether moiety will change into alpha beta unsaturated ketone. And then due to the presence of this alpha amino acid group, this amino group of the alpha amino acid will act as a nucleophile, and this will attack this alpha beta unsaturated ketone, and Michael addition of 1,2 Michael addition will take place, which will lead to a cyclic heterocyclic product of this type. So this type of bicyclic ketone will be formed as the product. Then another important application of Birch reduction is reduction of heterocyclic aromatic rings. So as we have seen that Birch reduction is used for the reduction of aromatic systems, this can also be used for the partial reduction of heterocyclic systems. So unsubstituted pyrols, they give good to poor yield depending upon the type of substrate which is used. Whereas if these unsubstituted pyrols, they are substituted by en-Vogt derivatives, then the yields of the reduction products improves drastically. Similarly, the Birch reduction can be extended to furan ring also. So for example, this substrate which is used in the synthesis of CSIR-NET, when the reduction of this system which is having a furan ring is done under Birch conditions in presence of sodium metal and liquid ammonia. So first this will be converted into this type of dihydrofuran ring. So one of the double bond will be reduced, and we will get this type of dihydrofuran, and in presence of this paramethoxybenzyl bromide, this will undergo alkylation to give us this type of stereoselective product. So the product formed is a very stereoselective product. As we start with optically active reactant, we are getting only optically active product. Then few more examples of Birch reduction. If we are using this type of heterocyclic system, isoquinoline derivatives, when they are reacted with sodium in liquid ammonia using THF as the solvent, then partial reduction of this carbon-carbon double bond will take place, and we will get dihydro isoquinolinic derivatives as the product. Similarly, if we use 1,3,5-triphenyl benzene, then partial reduction of this can also lead to formation of different types of products. So different types of cyclohexanes, substituted cyclohexanes, they can be formed, where the isomeric products they can be formed. You can see over here that in this enantiomer, this phenyl group is equatorial, whereas in this enantiomer, this phenyl group is axial in nature. So this is how we can get different types of isomeric products by the partial reduction of these types of aromatic systems in presence of sodium in liquid ammonia, using THF as solvent and ethyl alcohol as a proton donator substituent. So this is how different types of systems they can undergo partial reduction or Birch reduction. These are the various sources from which these examples have been taken. Modern methods of organic synthesis by Caruthers, then some NPTEL lectures and videos, then book on named reactions by JJD that has also been used for. In addition, some internet sources have also been used for preparing this lecture. Thank you very much.